In this video, I would like to begin to introduce the concept of an invertible matrix and the inverse of a matrix. Today we're going to focus just on concepts in theory, and in the next lesson we'll focus on how to find the inverse of a matrix and how to use that inverse once you have found it. Now, first of all, I want to emphasize that the concept of inverses in general is something that you're familiar with from the earliest days of regular algebra. In regular algebra, if you were given an equation like 2 times x equals 6, and you were asked to solve this equation and find the value of x that makes this equation true, you did that by multiplying both sides of this equation by the inverse of 2. The inverse of 2 being the reciprocal 1 over 2, also known as 2 to the power minus 1. If I go into this equation 2x equals 6, and I apply a 1/2 to both sides of that equation, then the 1/2 and the 2 will cancel each other out, and on the left side I'm left with just x. And then on the right side I'm left with the value of 3. So by applying the inverse to both sides of this equation, I found a single unique solution to this equation, x equals 3. Now, even in algebra, we understood that not all numbers have inverses, right? In particular, if I give you an equation like 0x equals 6, it does not make sense to try and solve this equation by applying the inverse of 0 to both sides of this equation, because trying to apply 0 inverse, trying to apply 1 over 0, 1 over 0 is not defined. Or in other words, 0 has no inverse. And because this was an equation that contained the number 0 that had no inverse, rather than getting a single unique solution, we have in this case an equation with no solutions at all, an inconsistent equation. 0 equals 6, impossible. So this has no solutions. Also, when we had an equation that contained this 0 on the left-hand side, it was possible to get infinitely many solutions and get something that's underdefined. If I have 0x equals 0, then this statement is trivially true. So this has infinite solutions. So this concept of inverses and using inverses to solve equations when possible is a familiar concept to us from regular ordinary algebra. And in this video, we're going to talk about what this idea looks like when solving matrix equations as opposed to solving ordinary algebra equations. So if you have a matrix A, it's possible that that matrix A has an inverse that we might call a to the power minus 1, the same way that we can think about 2 to the power minus 1. If you have a matrix A that has an inverse, then you can use it to solve equations, the same way that we use the inverse of 2 to solve this equation. If I take AX equals B, and I apply A inverse on the left side and also on the right side of this equation, then the inverse should have the ability to cancel out the original matrix in some way and allow us to find a unique solution, x equals A inverse times B. If a matrix A is going to have an inverse, and if that inverse is going to be useful in the same way that these inverses were useful, this is the kind of properties and utility that that inverse matrix should have. So based on that, here's a definition. If you have a square matrix A, the inverse of that matrix, what we call A to the power minus 1, satisfies the following property. If you multiply the matrix by its inverse, either on the left or on the right, you should be able to multiply them together and get the identity matrix. There's some other matrix out there so that when you multiply those two together on the left and you multiply those two together on the right, they essentially cancel out and they leave just the identity matrix behind. The identity matrix in this equation is playing the same role as when you multiply 2 by its inverse, you get the number 1. The number 1 in this context is equivalent to the identity matrix in a matrix context. If you have a matrix that has an inverse, it is called appropriately invertible. Whereas if you have a matrix that does not possess an inverse, the same way that the number 0 does not possess an inverse, a matrix that does not have an inverse is called singular, quote unquote singular. Now, when you think about the inverse of a matrix, I think it's helpful to think about it from the following perspective. The inverse of a matrix has to undo or reverse the action performed by the matrix A. For example, let me consider the matrix A, whose entries are 5, 0, 0, 5. I recognize this matrix from the work that we did at the beginning of the class. This matrix A would perform the action of scaling vectors by a factor of 5. So this matrix A is going to make vectors 5 times longer than they were originally. Now, if I wanted to undo or reverse that action, I would have to shrink the vectors and make them 5 times shorter. If I wanted to undo the action of this matrix A, I would have to scale vectors by a factor of 1/5. And the matrix that would do that is the matrix 1/5, 0, 0, 1/5. Let's check see if this matrix that I've written down is indeed the inverse of A as defined by this equation here. So let's go ahead and check. If I take the matrix A and I multiply it by the matrix A inverse on the right side, and I do that matrix product, the first row times the first column, that dot product would give me 1. If I do the first row times the second column, that dot product would give me 0. If I do the second row times the first column, that dot product would give me 0. And if I do the second row times the second column, that dot product would give me 1. So multiplied on the right-hand side, we have gotten the identity matrix as the result. So far, so good. If we reverse the order of the matrices and multiply by A inverse first and by A second, and I calculate the matrix product in this order, the result of that is going to be exactly the same. 1, 0, 0, 1, which is also equal to the identity matrix. So that's one way to understand the inverse of a matrix A. The inverse of a matrix A is a matrix that would undo or reverse the action of the matrix A. And if you bear that in mind, that understanding can help you to determine when a matrix has an inverse versus when a matrix might be singular. So let's talk about the conditions under which a matrix has an inverse at all versus the conditions under which the matrix would be singular. So this is a very, very famous theorem that I'm about to explore with you. This is what's called the invertible matrix theorem. The invertible matrix theorem is a list of conditions and properties that are held by any invertible matrix. So let's explore this together. So the first condition that must be satisfied if you're dealing with a matrix A that actually is invertible is that when you're going to solve matrix equations involving that matrix A, those matrix equations always have one unique solution. And the reason is that it forces the solution to this equation to be equal to exactly A inverse times B. So there's only one possible outcome to this equation when an inverse actually exists, and that is x is equal to the inverse times the b. So if you're in a situation where you're dealing with a matrix A and that matrix A has given rise to something with infinite solutions, or if it's given rise to something with no solutions, then a matrix like that cannot possibly have an inverse, because a matrix with an inverse always gives rise to a single unique solution when solving matrix equations. The other thing that you can check when you're trying to determine whether a matrix A has an inverse or not is you can think about like the action performed by A. Is that something that you can perfectly reverse? Is that something that you can perfectly undo? Or has the matrix A destroyed so much information? Has it compressed so much information that it's not possible to actually undo the action of A? So for example, if the action of A is just to rotate vectors, let's say 45 degrees counterclockwise, then this would be an action that is very easy to undo or to perfectly reverse. The inverse matrix would just perform the action of rotating the vectors back into place. It would rotate the vectors 45 degrees clockwise. By contrast, suppose that you had a matrix A that did a projection. If your matrix A is doing a projection, I think in this case that the inverse does not exist. Because if you take two vectors in two-dimensional space, it's possible to take two different vectors in two-dimensional space, and after projecting, they look exactly the same and they're completely indistinguishable. Because by applying the matrix A, we've lost the difference and we've lost the distinction between these two vectors. So this matrix A, this projection matrix, loses and destroys too much information, and so we are not able to perfectly reverse or perfectly undo that action of projection. I imagine it kind of like when you are making bread or making cake mix or something, right? Once you've cracked in the egg and put in the water and put in the oil and you've mixed all of that together, you are not going to be able to undo that action and separate out the cake mix and separate out the eggs and separate out the oil and separate the water. Once you've performed that action, there is no going back. And so that would be a situation akin to having a singular matrix with no inverse. Another sort of sign, another indicator of whether your matrix is invertible or singular, another sign comes from looking at the null space of A. You know, if your matrix A, its null space contains only the zero vector, then that's a sign that A is not compressing or losing any information. And so that indicates that the action of A can be reversed, which is a sign that A inverse exists. Whereas if your null space contained anything else besides just the zero vector, then that is an indication that your matrix A is compressing information. So you will not be able to reverse or undo that action. You've lost too much information to undo the action. Another way to understand invertibility is through the idea of rank. If you look at your rank of your matrix, the rank of an invertible matrix is always equal to the number of rows and columns. In other words, an invertible matrix is always full rank. Here you can bring the rank nullity theorem to bear here. If rank A is equal to the number of columns, then the null space has to be almost empty, and that's a result of rank nullity theorem. So that's another way to understand invertibility. If a matrix A is full rank, then it is invertible. If a matrix A is rank deficient, then it is singular, and no inverse exists. Based on what we saw yesterday, we can also say that the determinant of an invertible matrix must be non-zero. Because we saw yesterday, for example, that if the determinant of A is 0, then that's an indication that A is once again compressing information. That the null space of A does have extra stuff inside of it, that the action of A cannot be reversed. So that would be an indication that A inverse does not exist. Another way to understand it in some of the other language that we have used within this class, we could also say that every column of an invertible matrix A must be a pivot column. And this ties back to what we said earlier about rank, right? Every column of A is a pivot column is the same thing as saying A is full rank. And for the reasons we described earlier, that would mean A inverse exists. Yet another way to understand this is through the lens of range and column space. If the range and the column space of A is the same thing as the codomain of A, then we can also conclude that A is invertible in this case. So the explanation for this property is that remember that when we're talking about invertible matrices, we're only talking about matrices that are square. N rows, and therefore also exactly n columns, however much that happens to be. Which means that the domain and the codomain of this matrix must both be n-dimensional space. So if you have a column space of A, if your A has a range that's smaller than this, then again, rank nullity theorem kicks in to say if the range is smaller in its dimension than the domain, then A must be losing some information. And so once again, in a situation like that, A inverse would not exist. So that's another way to understand invertibility. If your matrix A is invertible, then the range is equal to the codomain and it's equal to the domain. All of those would be exactly the same n-dimensional space. But if your matrix A is singular, if your A is doing some kind of compression action, then you will see the range being smaller than the codomain and smaller than the domain of the matrix. Yeah, we're going to keep going, folks. We're going to keep going. When we say that the columns of A span Rn, that's really just another way to phrase the property that we have said up here. The column space is everything that is spanned by the columns of A. The columns of A span Rn. That's the same as saying that the column space of A is equal to Rn. So this is just another phrasing of this property. We could also say that the columns of A must be linearly independent. The columns of an invertible matrix must be linearly independent, and a lot of the reasoning behind that property came up back here in the checking for linear independence lesson. We saw that if you build a matrix from a collection of column vectors, if those column vectors are linearly dependent, then the matrix A has something that's non-zero in its null space. So that would be a red flag for a matrix who's trying to be invertible. A matrix that's trying to be invertible cannot have any non-trivial vectors in its null space. So such an A cannot be invertible. Finally, we can think about this through the lens of what does your matrix become when it is row reduced, when it is written in reduced row echelon form. So the final way to understand an invertible matrix is that when you row reduce it, the reduced row echelon form of A is the same thing as the identity matrix. Let's think about that versus if our A tilde had any other shape. Versus, for example, if we had a row of zeros on the bottom. If we had some non-zero entries, maybe over here in the third column. When we look at these two matrices that I've written down here on the right-hand side, we can see for sure that something is wrong in terms of, for example, their rank. The two matrices that we've written over here on the right side after row reduction have only ended up with two pivots. And because there were only two pivots, only these first two columns of the matrix were pivot columns. So both of these are rank deficient. So the matrix A would not be invertible in this case. But by contrast, if you do row reduce your matrix and you get something that looks like the identity, then from this formation, you can see that this guy has full rank. So this would be invertible. So these are several different ways to understand or to check whether a matrix is invertible or not. You can think about what kind of solutions that you're getting from equations involving A. You can think about whether the action of A can be reversed or undone. You can think about whether the null space of A contains only zero. You can think about whether the matrix A is full rank. You can think about whether the matrix A has a non-zero determinant. You can think about what you're seeing in terms of A's pivot columns. You can think about what you're seeing in terms of the range of the matrix, in terms of the span of the columns, or in terms of the independence of the columns. And you can also think about what A looks like after it has been row reduced. This theorem that we are exploring here today, this so-called invertible matrix theorem, is incredibly famous. You can see on Wolfram Math World, for example, the invertible matrix theorem written here, and I think they've given even more conditions for invertibility than what we have given in our notes. 23 conditions in total, each of which can be used to check whether a matrix A is invertible or not. You should be able to justify and explain all of these properties from the conceptual work that we have done up to this point. But in practice, the ones that I think are most useful, the easiest condition often to use to check whether a matrix is invertible or not is to see if the determinant of the matrix is non-zero. In some cases, for certain matrices, especially matrices coming from transformations, this property here, in terms of the action or effect of A, can also be a nice one to use. Those are the two, in my opinion, really essential properties here for checking. One is to just check the determinant, and two, if your matrix A is coming from a specific transformation, an action or effect that you understand well, it can be easy to think about whether that action or effect can be reversed. So for a quick example, let's go back to this matrix that we've studied in great detail. This matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's make a conclusion. Is this matrix invertible or is it singular? So we've done plenty of work up to this point to help us to answer this question quickly. All the way back in our matrix arithmetic module, we calculated the determinant of this matrix. And we found in that lesson that the determinant of this matrix is 0. Because the determinant of this matrix is equal to 0 exactly, we can conclude right away that this matrix is singular and it has no inverse. We have worked with this same matrix in many other lessons. So let's see how we could draw that same conclusion from some of the other work we've done on this matrix up to this point. For example, when we worked with this matrix in the null space lesson, when we row reduced that matrix, the row reduced version of that matrix was not the same thing as the identity. So that's another way to see that this matrix is not going to be invertible. When we studied the null space of the matrix, the null space had non-zero vectors inside of it. So that's another way to see that this matrix A is not invertible. When we studied this matrix and we solved equations like AX equals B, we saw that this equation had infinite solutions as opposed to having a unique solution. So that's another confirmation that this matrix A is singular. When we studied this matrix in the column space lesson, we saw that this matrix was rank deficient and only had a rank of 2. The column space is too small, and so on and so forth. So using any of those properties, also a rank deficient, also column space smaller than R3, also does not become identity when row reduced, also has non-zero vectors in null space, etc., etc. All of these would be other ways to detect that this matrix A is singular. So that concludes this lesson. The inverse of a matrix A is another matrix that is designed to cancel out or to undo what the matrix A has done. The inverse of a matrix is characterized by if you multiply a matrix by its inverse, those guys cancel out and you just get the identity. Now, thinking about whether the action of a matrix can be reversed or not can help you to determine whether the matrix has an inverse at all. If you have a matrix A, for example, whose job is to scale vectors by a factor of 5, that can be reversed pretty easily. Just scale by a factor of 1/5. If you have a matrix A that is doing rotation in one direction, you can invert that by just rotating in the opposite direction. So that's one way to think about whether a matrix A has an inverse, and it's one way to think about what that inverse might plausibly be. But the invertible matrix theorem gives us lots and lots and lots of other conditions that we can check to see if a matrix A is invertible or not. For example, you can look at solutions, you can look at null space, you can look at column space, you can look at rank, pivot columns, etc. And you can also look at the determinant of a matrix, because the determinant of a matrix is equal to 0 when the matrix is singular.